Alright, so for this then we're looking at Markovnikov's rule, and in particular we're talking about this rule with reference to hydrogen halides. Okay, so this basically means we're talking about halogens that are bonded to hydrogen. So for instance here we have the chlorine, which would be a halogen, and you would have bromine as well as iodine. Alright, so there you see what I mean then. The halides, chlorine being one of them, I've just circled those two in green just so you can link the two of them together. Hydrogen halides then is what we're calling this. And Markovnikov's rule then operates around these hydrogen halides. This is the key thing, okay? Now, in the addition of HX to an alkene, where of course that X right there, that stands for one of these halogens that we're talking about, and this is the H that precedes it. Well, what it says here is that the hydrogen attaches to the carbon with fewer alkyl substituents, and the halide attaches to the carbon with more alkyl substituents. Okay, so I mean, look at, if you look at this, this is the one with more alkyl substituents, this carbon is, and this carbon has the least amount of carbon or alkyl substituents. Okay, but look at a simpler way just of stating that would be that, look at that the hydrogen attaches to the carbon that already has a lot of hydrogens attached to it. Okay, so it has a higher propensity to attract hydrogens. That's the key thing there. So the hydrogen will be attracted to this carbon with more hydrogens because it already has established this path already. And the halide will bond to the other carbon with the other alkyl groups. So, you know, whichever way you prefer, but it's a little simpler to think that that the hydrogen attaches to the carbon with more hydrogens at the reaction stage of this. Okay, let me just preface it to say as well that the product that's formed then from this, well, you can see here's the product. The hydrogen from over here has indeed bonded with the carbon that had the most amount of hydrogens present, and the chlorine has attached to the other carbon. Okay, so this is just an overview of the reaction before we go into some detail about the mechanism. But just to preface this, as I said, we want to say that this carbon, meaning this one here, will get a share of electrons from the carbon-rich carbons on either side of this carbon. So that's an important thing to remember, that this carbon here is going to be willing to give its electron away, and this kind of explains Markovnikov's rule. That's the point about it. This carbon is more willing to give its electrons away than this one right here, because this carbon has no other carbons around. Well, okay, it's got one carbon to this side, so that makes it a primary carbon, whereas this carbon right here, it has a carbon on either side. Okay, so that makes it a secondary carbon, and in fact here with this other carbon it makes it a tertiary carbon in the end, but in the middle phases of this we're talking about a secondary carbon. Okay, so to the mechanism then for the reaction. Okay, so look at, in this mix it is well and easy to imagine that, okay, here's our alkene here, longest chain being 3 C's with the double bond, so it's an alkene, methane, ethane, propane, so it's a propene I should say, alkene with a methyl group, and all that jazz. But the point about it is, anyway, I've just made some references here. Here's HCl then in the mix as well. Okay, the chlorine is going to have a partial negative charge. It's highly electronegative, so it's going to take most control of the electron that in the bond, that is, between the H and Cl. So it's going to be partially negative, whereas the H is going to be partially positive. Okay, But it's still even more easy to imagine that in some cases the electron is just going to be taken entirely by this highly electronegative chlorine, and so in that case then we're going to have a chlorine that is completely negative and a hydrogen which is going to be completely positive. It's basically going to be a proton because the hydrogen will have no electron, so it's basically just a single proton in that case. And then we have to see what happens. Okay, so now we have the situation where the chlorine has completely taken control of that electron. The hydrogen has become separated, unbonded anymore to the chlorine, and it is just basically a proton. It's a positive charge. So with this being the case, then we've got to say, well, okay, things have changed a little bit now. This hydrogen now is going to be in a position where it is actually looking for electrons now. Okay, so this makes it become what's called an electrophile. It's looking for electrons. Okay, now where in this picture then do we have an abundance of electrons? Okay, so what I've done is I've colored a bond pair of electrons between these two C's, but the point about it is that we've got a double bond right here, and a double bond means that we're electron rich in this area. Okay, so therefore where these bonds occur, it's certainly the case that we can, and this is what indeed does happen, one of the double bonds breaks, and one of the electrons then, well, the bond when it breaks means the bond is dangling and it needs to bond with something else. And what does it bond with? Well, it bonds with a thing that needs an electron, and guess what? The H plus needs an electron, so that's where the bond takes place. So this is a nucleophile. This is the one that wants to give away its electron. Then in that case, this wants to accept an electron, so this is the electrophile, and that is the bond that does take place. And you see that over here then we've ended up with this electron, so I'm just going to color code them in so we can see that change right there then, if you just bear with me. Alright, so over here then you can see on the product side here we do have that bond, that dangling bond that was there has now bonded with the hydrogen. So we have the electron that was here is there, and this electron that was here is now donated to the H, because the H needed an electron to neutralize it, positive and negative being attracted to one another. Okay, so that's all very well to talk about that, but there's also somebody else showing up here. And who else is showing up? Well, it's the chlorine that we have here as well, okay, with his powerful negative charge now. So chlorine has to be dealt with now at this point as well. So chlorine is negative, which means then it's looking for a region that is now positive. Now, of course, over here we had 1 bond, 2 bonds, 3 bonds, and 4 bonds. That meant that we had 4 electrons on the valence shell, if you like, of this carbon. Now, when this one here got dislodged and bonded with the hydrogen, that meant that we had 1 less electron, 1 bond, 2 bonds, and 3 bonds only remaining now, the single bond there. Well then, if we've only got 3 negative electrons there instead of 4, we don't have a neutral carbon anymore, because now we have more positives, or more protons if you like, in this carbon than we do have electrons. So therefore it maintains a positive charge and it becomes what's called a carbocation. Now, given that this is positive and our chlorine is negative, well, it makes all the good sense in the world for the chlorine to scuttle on over and to bond with this carbon and make the whole thing neutral, if you like. And that is the next phase of this then. So we're looking at, yes, this is exactly what we're looking at. We're looking at this product then, where the chlorine has now bonded with this carbon, this hydrogen has bonded with this carbon, and now we have a situation where we have a carbon here that is bonded, as we say, to 1 carbon, 2 carbons, and 3 carbons, and that's what's known as a tertiary carbocation. Or at least this carbocation up here is the tertiary carbocation. It's bonded to 1 carbon, 2 and 3 carbons there. And this is the point that I made at the beginning then, that this is the carbon that is most likely to donate its electron, as it did to this hydrogen here. And it's likely to do that because it's surrounded by as many carbons as possible, and these carbons are electron rich and in a position to possibly share electrons with this carbon, that being the case. However, with the presence of the chlorine, we get a bond straight away, positive and negative, happening there. But this is the reason why Markovnikov's rule is the case, that the hydrogen bonds to this carbon and not to this carbon. This is the, I should say, this is the majority product. 95% of the product will consist of this, with the chlorine bonded to this carbon with more alkyl groups, and this hydrogen bonded to the carbon with more hydrogens. This is the 95% majority product. There is a 5% of the other where the chlorine is bonded here and the hydrogen is bonded here, and this was determined experimentally, but the whole reason for that then, Markovnikov experimentally looked at that, but the whole reason for that was because of this sharing of electrons. This carbon is more likely to donate its electron, as in this electron here, to the hydrogen, because of the presence of carbons around it, electron rich and in a position to share. And that is the whole reason for why Markovnikov observed what he observed.